All right, folks, this is going to be a problem from exam 2. It's problem number 22 from exam number 2, and this has to do with confidence intervals. Okay, so here's the problem. Average number of mosquitoes caught in 64 mosquito traps. So obviously N is 64. In a particular environment was 700 per trap. So that's my X bar. Average number gives us a pretty good clue that that's our X bar. The standard deviation of mosquitoes that it was caught in the entire population is 100 mosquitoes. So that's my sigma, right? So they're kind of giving you a big clue there that the population is known. The population sigma is known, and that's 100. What is the 99% confidence interval for the true mean number of mosquitoes caught in all mosquito traps? So let's just take a second here to kind of visualize or to look at the big picture here, okay? The entire population, the entire population is all traps, right? Or maybe you would say all mosquitoes caught in all the traps. That's your entire population. That's too hard. There's no way for us to figure that out, right? We can't go out there and check every single trap that's out there. So what we do is we take a sample, and from this sample we get our X bar. We find out what the X bar is for the 64 mosquito traps. And what we hope for is that the 64 traps that we actually looked at randomly reflect the entire population. So this is a common situation that we're in real life, because we can't possibly find out what we want to know from the entire population. So we take a sample, and once we get this sample, we get the sample statistics, and we use this sample statistics to estimate the population parameters. So remember, there's a difference between a statistic and a parameter. So look it up if you forgot, okay? All right, so let's take a look at this problem. I'm going to go ahead and close this out. Okay, so here's my handwritten solution to this problem. This is exam number 2, problem number 22. This is a confidence interval is what we're looking for this mosquito problem. All right, so this is the information we're given. Got the X bar, we got the N, we got the sigma. And in this particular case, according to the problem, the population standard deviation is known. So it's the standard deviation is 100. We want us to find the confidence interval of the population mean, the 99% confidence interval. Okay. All right. So in this problem, we know the population standard deviation. That's given to us. We want the confidence interval of the mean. So this is a problem for which we use section 7-1 techniques. Okay. So let me take a look at those formulas. Give me a second here. Okay, so this is from chapter 7. This is the important formulas. Now, what I have is I made a photocopy of all of these pages, and I put them in a little pamphlet that I call my cheat sheets. I recommend that you do the same thing. If I get a chance, maybe I'll email mine out. But you should have your own with your own notes on it and the things that help you. So in any event, this is chapter 7, and chapter 7 talking about intervals. And here's the formula for the confidence interval of the mean when sigma is known. Okay, if you don't know sigma, then you don't use this formula. And that's what he's talking about here. It is very confusing. Now this is just a formula page. The real discussion is in the textbook on page, oopsie daisy, on page 386. Okay, it's right at the very end of section 7 whatever section this is. Okay, yeah, this is section 7-2. Okay, he has this little discussion here at the very end of 7.2, just before the applying the concepts. It's kind of confusing, and absolutely very confusing if you just look at the formula page that I gave you. So you have to kind of look this over, okay? What it kind of boils down to is that Sometimes we use the Z distribution, sometimes we use the T distribution when we find these confidence intervals, okay? They look very, very similar. Let's take a look here. Give me a second. Let's see. Okay, so you take a look here. It's the mu's in the middle for both of these, and it's x bar plus x bar minus this guy right here. This is the margin of error. Well, what's the difference? You got this coefficient here. You got this z value, and you got this t value here, and then it's multiplied times this, which is something on top and the square root of n on the bottom on both of those. So as you can see, they're very, very similar. Well, remember that as n gets large, t becomes closer and closer to being the z distribution. So for a large n, they're basically the same. They're close enough for government work to be the same, okay? So whether you have a z-score, the z value, or whether you have the t value, they're going to be getting closer and closer to being the same as n gets larger, okay? So in my opinion, the better approach is just to say, listen, if you know the sigma, if you know what sigma is, this is the formula you use. If you don't know what sigma is, you use S. You use this sample standard deviation, okay? Now he's got all these nuances here that probably a good idea to be aware of, but as far as actually using them on the exam, I don't see that. So he says students sometimes have difficulty deciding which one do you use, the Z or the T. If you know sigma, you use the Z, and it doesn't matter what the sample size is, as long as the variable is normally distributed. Well, suppose it's not normally distributed. Well, then if you have n greater than or equal to 30, you can still use it. So if you know sigma, you use the Z, okay? If you don't know sigma is unknown, but n is greater than 30, then you can use S in the formula, but you're going to use the T formula, the T values for that coefficient that we were just looking at. For that, you're going to use the T. This is called a coefficient. This T coefficient rather than the Z coefficient. Okay, all right. So far so good. We're making sense. Finally, if sigma is unknown, so you would expect to be in the T category, the T coefficient category. If n is less than 30, if it's a small sample size, we're going to definitely use the S. We're going to use this guy here. Okay, we're going to use that. But there is a requirement. The variable has to be approximately normal. And that kind of makes sense, doesn't it? I mean, if you have a small sample size, I mean, gosh, why would, if it's approximately normal, things will work out. But if it's not normal, if it's not approximately normal, then it's not going to work out. Okay, so here's the summary of the rules. Do you know sigma or do you not know sigma? If you know sigma, here's the rule. Okay, use the Z values. If you don't know sigma, we're going to use the T coefficients and we're going to use S. Okay. But if it's a small sample size, you're stuck. If it's a small sample size, the variable must be normally distributed. If it's not, you really can't use these tests. We have to find something else to do, or you say, hey, I need more data. There's nothing wrong with that. Okay, so let me get back to the problem that I was working on. Okay, and this problem that we're working on, this is the mosquito problem. We know the population standard deviation, so we know for sure that it's going to be the Z distribution we're going to use. The Z test is another way of saying that. N is 64, so we're in wonderful shape. N is greater than 30, so we can use this test no problem whatsoever. Okay, all right. So Z sub alpha over 2, that's the Z value that gives us an error budget of 1%. Now, where does that 1% come from? That's what they told us. They said they wanted to have a alpha, they wanted it to be 99% confidence level. So it has to be 99% confidence level. So 1%, the alpha is 1%. is a interval test, so it's always a two-tailed test if it's an interval test. So we can be wrong over here, we can be wrong over here. So 1% total error budget means that there is 0.5% over here, 0.5% over here. So we got to find the appropriate z-value. So the appropriate z-value is 2.58. Well, that just comes from the formula, or excuse me, that just comes from the tables. Okay. Okay, now I hope you've done this a million times, so this is kind of boring for you, me showing this to you, but let me, just in case somebody is still having a problem with this. Why is it 2.58? Well, remember, I want that error budget to be, it's so hard to do this because I can't show two at the same time. Give me a second here. Give me 1 second here. Okay. So this error budget is 0.005. Okay, so 0.005 over here, 0.005 over here. Add them together, you get the 1%. Okay, so you want 0.005 over here. Well, what does that translate to? What that means then is 0.005 to the right means that it is, oh gosh, it's just impossible. I can't get all of these on the same page. Give me a second. Okay, if you want 0.5% to the right, that means that it's 99.5% to the left, right? It's 99.5% to the left. So you look here and you find it, and I'll just go right to it. Here it is. It's 99.5% to the left. What is that? 2.5. We come here. It's in this column right here. 2.58. So that's where that number comes from. I hope you've done this a million times, so you really didn't need me to explain this to you. Oh boy. Okay, so that's where I get the 2.58 as my critical value. Boom, there it is. And it's plus or minus 2.58. All right, so we use the formula on page 372. Okay, remember the margin of error is just this 2.58, the z sub alpha over 2, times this guy. This guy is normally called the standard error. So the standard error times this coefficient gives me the margin of error. Okay, so here's the interval. The interval is mu is between, it's less than x bar plus the margin of error, and it's greater than x bar subtract the margin of error. So it's plus or minus the x bar. Mu is plus or minus, in the interval plus or minus x bar plus or minus margin of error. It's so hard to say, but it's so easy to write. Okay, so here it is. The margin of error is the 2.58 times this standard error. Crank it out, get your calculator. Boom, there it is, 32.25. So the x bar we got from the information given to us is 700. So it's 700 plus 32.25, and it's 700 take away 32.5. Crank that out, and here's what you get. You get this, and you get this. But we're talking about mosquitoes, right? You can't have 0.25 of a mosquito. So you have to round everything off. So you round it off. So it's 732 over here, 668 over here. They're discrete variables. It's the number of mosquitoes. And we're going to use the round off rule that actually is on page 373 if you want to look at it. Okay, so that's the end of this tape. I hope that helped. I got to turn this thing off.